Alright, in this lesson we're going to be talking about geometric sequences. So sequence is geometric if it can be written in this form, where our initial term is a and our second term is a times some value r, and then we've got ar squared, ar cubed, and so on. So any term can be written a times r to the n minus 1 power. That r is some non-zero constant r called the common ratio between two terms. Okay, to find that common ratio, you can take any term and divide it by the previous term. Okay, that'll give you the common ratio r. Okay, our two main forms of geometric sequences, we've got our list here. Our explicit form, we can write any geometric sequence in this form where we've got our initial value, a sub 1, and we multiply that times our common ratio raised to the n minus 1 power. Recursive form for any geometric sequence can be written as our initial value first, and then for our formula, a sub n equals our previous term, a sub n minus 1, times our common ratio r. Or it can be rewritten with the r and as the coefficient of our previous term. Okay, and of course that only works for n values bigger than or equal to 2. Okay, let's look at a couple examples. All right, let's say you're asked to find a recursive and explicit formula for the following sequences. All right, example 1, we've got 3, 6, 12, 24, 48, and so on. Okay, so what we want to do first is note our initial value. So 3 is our initial value. Then we want to find our common ratio. So we can find what number we multiply a certain term by to get the next one. So 3 times 2 is 6, times 2 is 12, times 2 is 24, times 2 is 48, and so on. So make sure that it works with each term in the list that you're given before you determine that it is a geometric sequence. You can also, like I said on the previous board, you can also take any term and divide it by the previous term. So if I take 48 divided by 24, that's 2. 24 divided by 12 is 2, and so on. Okay, so we've got our initial value, we've got our common ratio. So now let's write both forms of this sequence. Explicit form, we got a sub n equals our initial value, 3, times our base, our common ratio, 2 to the n minus 1 power. Now, what kind of a function does that look like? It looks just like an exponential function, doesn't it? And if you were to graph this sequence on a graph where n versus the actual term, then it would look like an exponential, in this case, an increasing growth function. Okay, so remember, arithmetic sequences model linear terms or linear functions. Geometric sequences will always model a exponential function. All right, so recursive form. We've got our initial value, a sub 1 equals 3, and our function or our formula, a sub n equals 2, which is our common ratio times the previous term, a sub n minus 1. All right, our second example, example number 2, we're given a different list. We've got 10 to the negative 3rd power, 10 to the negative 1st power, 10 to the 1st, 10 to the 3rd, and so on. So again, identify your initial term. Initial term is 10 to the negative 3rd power. Our common ratio, to go from here to here, we can multiply by 10 squared, or 100. Okay, you're welcome to rewrite these without exponents if it helps. Multiply this by 10 squared to get 10 to the 1st, 10 squared to get this. Okay, remember when we multiply two powers with the same base, we add the exponents. All right, so common ratio is 10 squared. So our two formulas, explicit, we've got our initial term times our common ratio to the n minus 1 power. So you can write this as 2n minus 2 or just leave it factored out, either way. And recursively, we've got our initial term 10 to the negative 3rd, and we've got our function a sub n equals our ratio times the previous term. So we're just multiplying that last term by whatever our common ratio is to get the next term. All right, look for some more videos with more examples of arithmetic and geometric sequence problems.